I'm Christine Turner,
I'm Courtney Hammonds.
and we're presenting on Experiment 1, Introduction to Spectrophotometry, the Absorbance of Cobalt Chloride.
Okay, so my presentation is going to include the introduction, the experimental, the results, the discussions and conclusions, and of course our responses.
Okay, so the purpose of this experiment was to use the percent transmittance and the absorbance found from the spectrophotometer at several different wavelengths ranging from 400 nanometers to 600 nanometers in 25 nanometer intervals to determine the lambda max of cobalt chloride. And then from the lambda max we could graph the standard curve and determine the concentration of the unknown solution of cobalt chloride.
So spectrophotometry can determine the concentration within a solution, and it's how the properties interact with reactions. So all it is just how much light is absorbed within the sample. So we use Beer's law. This is absorbance equals epsilon times concentration times path length, and all it is just a relationship between the absorption and the concentration.
Okay, so spectrophotometry was the method used in this experiment, and using spectrophotometry we could determine the lambda max, which is the wavelength at which the absorbance is highest, and from that lambda max we could make further conclusions.
So what we started out with was 2 cuvettes, and we filled 2/3 of the way with water, and the other 2/3 of the way with cobalt chloride. And the deionized water was considered the blank. It was wiped, and it was used to calibrate the spectrophotometer. And we would use the cobalt chloride to get the readings of transmittance and absorbance for wavelengths between 400 and 600 nanometers. This incremented by 25 nanometers, and the blank was used to recalibrate each time that we would find the transmittance and absorbance for the cobalt chloride. It was determined that 500 nanometers was the lambda max.
Okay, so in this experiment 8 different cobalt chloride dilutions were made with differing volumes. All of the 8 solutions totaled 5 milliliters, and between each one the spectrophotometer was recalibrated with the blank again, and it was set to the lambda max wavelength to be read for all 8. And from there we could determine the standard curve.
So we were each given an unknown concentration of cobalt chloride, and we would run through the same steps with the blank. We'd wipe it off, put it in to recalibrate, and we would use the lambda max of 500 nanometers to test for the absorbance and transmittance of each sample. From there we were able to figure out the concentration.
So this is table 1, and it just shows us that for the wavelengths, we could see here at 500 nanometers is where the transmittance is the lowest and the absorbance is the highest. So the transmittance would be a U shape here, and the absorbance is like a bell shape.
So we have a calculation for the absorbance of 400 nanometers. We start out with absorbance equals 2 minus log of percent transmittance. So absorbance equals 2 minus log of 87.2, and absorbance equals 0.0595.
And this is just showing absorbance as a function of wavelength, and we can see that the highest point is at 500 nanometers where the absorbance is the highest, and so we can conclude that that is the lambda max wavelength.
So here we have our charts of the 8 test tubes that we did. You can see that we have the different solutions that all go up to 5 milliliters of deionized water and cobalt chloride. We also have the absorbance, the transmittance rate, and the concentration. So as you can see that there is a correlation. As she said, the percent transmittance will decrease as the absorptions increases. Also, you can see that both the absorbance and the concentration have a parallel increase together, so they follow one another.
Here is an example molarity concentration for test tube 3. and it says the molarity of the concentrated times the volume of the concentrated equals the molarity of the diluted times the volume of the diluted. And so we know that the molarity of the concentrated was 0.150 molar times the volume for test tube 3 was 2.00 milliliters. And we set that equal to the molarity of the diluted, which is what we were solving for, times the volume we were trying to obtain, which is 5.00 milliliters. And using algebra, we could determine that the molarity of the diluted solution would be 0.0600 molar.
So here we have an example calculation for epsilon with test tube 3. So here's Beer's law like we spoke before, and it's absorbance equals epsilon times concentration times path length. We're looking for epsilon, so we switch our equation, and we get epsilon equals absorbance divided by concentration times path length. So epsilon, we do our math, and we get epsilon equals 5.80 liters per mole centimeter.
Here shows the standard curve that we obtained from all of the cuvettes being read at the lambda max wavelength. And we can see it's a linear function that absorbance increases as concentration increases. And from this line, we obtain this equation of the line. And this correlates to Beer's law, which is absorption equals epsilon times path length times concentration.
So here's our chart for our unknowns. We have unknown 8, which transmittance is 33.8, absorptions is 0.470. Unknown 9 has the transmittance of 29.0 and absorption of 0.536.
This is the calculation for the first unknown we had, unknown number 8, and we use the equation of the line from the standard curve and changed it to the Beer's law equation. So we plugged in the absorbance of our unknown for our test tube into the A right here, and using the math we did the equation and we ended up with the concentration being 0.0887 molarity.
So here's unknown 9, and it's the exact same steps that she did except for the absorbance is different. 9 was 0.53, so we plugged it in, and the concentration is 0.101 molarity.
Question 1 of the discussion asked about the relationship between percent transmittance and absorbance, and we could tell from table 1 that the percent transmittance and absorbance had an inverse relationship, because we can see as percent transmittance decreased, absorbance increased, and then once it hit the lambda max, percent transmittance started increasing and absorbance started decreasing.
So question 2 is the 500 nanometers is the correct select for lambda max, and this is a very simple correlation, as you can see. As we get higher with our absorbance, peak wavelength is at 500 nanometers, so we get it lambda max.
And so the relationship between absorbance and concentration was a direct relationship. And if you look at Beer's law, that makes sense, because as the concentration increased, which is right here, C, that would also increase absorbance. And so basically the higher the concentration, the less light passes through in the spectrophotometer, and the absorbance is increased as well.
So as it was pointed out before, there is the correlation between percent transmittance and absorbance, as well as absorbance and concentration. As we pointed out, as absorbance T gets smaller, absorbance gets higher. The same with the parallel increase of concentration and absorbance. So it was determined that the wavelength that we just went over about the correlations, so it was that 500 nanometers was highest because it correlated best with the highest absorbance. And the 2 unknown concentrations were figured out using Beer's law. So the molarity of unknown 8 was 0.0887, and unknown 9 was 0.101 molarity as well. And that's
And
our
these are,
references.
thank you.